Hi there, welcome to my channel Mandu to Fundu. In this video, I am going to discuss about the solution for finding the right side view of the binary tree. Let's look at the problem description. We are given a root of a binary tree and we have to return all the nodes that we can see from the right side of the binary tree. So in this case, we can see 1, 3 and 4 if we are standing on the right side of the binary tree and look at the tree. The number of nodes in the tree is in the range 0 to 100. And the node values can vary from -100 to 100. Let's see how we can get the right side view of this tree. So the input we have is this. We have to perform the level order traversal on this tree, and at each level we have to add the value of the last element visited on that level to the output list and finally return the output list. So in this case, this is level 0, so the node 1 is the last one, that is the only one, so that is the last. We added that to the output list, and at level 1 the node 3 is the last one visited, so 3 is added to the output list, and on the level 2 node 4 is the one last visited, so 1, 3, 4 is now present in the output list and we return the output list. Let's look at the flow chart. Input for this procedure is pointer to the root node. First we initialize the out list and the last variable. Then we check whether the root node is null. If so, we return the empty list. So we return the empty list. If the queue is not empty, then we count the number of elements in that queue. And then we initialize the count and the index variable. Basically, we will loop through all the elements present in the queue at this point in time. If there are only count number of elements is there, then we process only that count, because in the middle of the loop we keep adding the left and right child. So but still we will limit the processing only to count, so that we process only the elements in that level. So we are entering the inner for loop where we check the index is less than count. If so, there are some elements present. We dequeue the first element and assign that to the variable last, and we check whether the dequeued node has a left child. If so, add that to the queue. Same way, if the dequeued node has a right child, we add that to the right child, and then we increment the index. That loop will process all the nodes present at that level. Once that is processed, all the nodes are processed, we break out of this loop, and then we add the value present in the last node to the out list, and then we attempt process the next level of element by checking this condition. If the queue is not empty, that means the next level has some element. If the queue is empty, then we are done. We have processed the entire tree. So this will repeat until we meet the conditions when the queue is empty. Then we will come out, and finally the out list has all the elements present in the right side view. Let's move on to coding. First I initialize the output list, and then I check whether the root is null. If so, we return the empty list. otherwise. Then we initialize the queue with only one node, which is the root. And then I declare the variable for tracking the most recently processed node at each level. Now so this is the outer loop which runs as many levels the tree has. Then once we once we loop through that all the elements in that level. While we are processing, we always are updating the last variable with the most recently processed element. So we assign the current node to the last variable, and then we check whether the current node has the left child. If so, we add that left child to the queue. And if the current node has the right child, we add that right child to the queue. So when this loop ends, the queue will be having all the elements present in the next level. Then once we come out of that loop, we add the value of the last node into the out list, so that we have finally the right view of the. Now I am going to run the test. Okay, it's accepted. Now I am going to submit this program. Cool, it's accepted. Next I am going to do the code walkthrough with sample input. We have this input. In this tree, the right side view will be 5, 4, 6. So that is what we are expecting as output. Let's see how this code generates this output. First, we initialize the queue with the root node 5. Okay, and then we enter the outer for loop where we check whether the len of q is greater than 0. The condition met. So we are entering, and we process at that moment how many elements in the queue. Only that many number of nodes will be processed. For example, in this level, at this level, this is the only node present, so this inner loop runs once. Okay, so we dequeue the element, and then we track that element through the last variable pointer. So the last variable keep track of the most recently processed node, and then we check whether that current node has a left child. If so, we add that left child to the queue, and same way we check whether the right child exists. If so, we add that to queue. So this loop continues until the count number of nodes processed. So when we come out of this loop, the last node processed will be present in the last node. So we add that value to the out list. So in this case, 5 is added to the out list. So level 0 processing is done. Now, so while we are processing, we added these two nodes to the queue. So now we are going to process in the next outer loop iteration. So in this case, we process, so the queue contains 1 and 4. So we enter this inner loop, and there are two elements. So this loop run 2 times. So we dequeue the element and then check whether it has a left child or right child. In this case, this node do not have any left or right child. So next we process the node with value 4 and we assign that to the last variable, and then we check whether it has a left child. Yes, it is. We added that to queue, and then also we check whether it has a right child. Yes, it is. So these two nodes will be added to the queue. So when we come out of this inner loop, the last variable points to this node, and we add that node's value to the out list. So we now completed the level 1 processing. So the queue right now has only these two nodes in it. So 3, 6. So again we are entering the inner loop to process that two nodes. So the last node points to the most recently processed node, and we check whether the current node has a left child or right child. In this case, there are no left or right child. So we process the next element and we assign 6 to the last, and then we check whether it has a left or right child. This also do not have any left or right child. So we break out of the loop because we processed those two nodes, and then we add the value present in the node which is pointed by the last variable to the out list. So right now the out list has 5, 4, 6, 5, 4, 6, and then when we come back to the outer loop, the queue is empty now. So we break out of the loop and then we return 5, 4, 6. Next, I'm going to do the time and space complexity for this solution. I'm going to use this input for the time and space complex analysis. So for this input, we have to traverse the entire tree, and then at each level, the last processed element will be added to the out list. The outer loop covers levels, and the inner loop covers the processing of nodes at each level. So for the first iteration, this inner loop runs once. In the second iteration, this inner loop runs 2 times. The third iteration, this inner loop runs 2 times. So totally it runs 5 times, which is the total number of elements in this tree. So the time complexity is order of n. We are using this queue data structure to capture the node at each level before start processing for that level. So at each level we need certain number of elements. Depending on the level, the number of elements in the queue varies. For example, if we have a tree with height 0, only one node, then we need the queue of size 1. If we have the tree with the height of 1, we need maximum size of 2, because when we process the level 0, we need space for one element. When we process the level 1, we need space for 2. Maximum we need 2. Okay. Similarly for the third level, height 2. So assuming the tree is complete binary tree, meaning this has 4, this has left child, right child, this has left child and right child. So totally here we get 4 nodes. So at that point this queue needs space for maximum 4 elements. So if we extend that, a tree with height h needs space for the 2 to the power h nodes. So h is the height of the tree, so which is nothing but log n base 2 when the tree is complete binary tree. So the space complexity is 2 to the power log n. Thanks for watching this video. Have a great day.